Hello, everybody. Today's lecture will be about delay and or dead time. Now, up to this point, we have looked at controller design for linear systems. We had some kind of a transfer function, and the assumption was that if you apply any input to a system, the output directly responds back without any time difference. Now, of course, this week we will look at the case where we have a noticeable delay. So there's a time difference. If we apply an input to a system, then there's some time that passes, and after the time, suddenly the system gives an output. So therefore, we will look at a delay, and this delay is modeled in the time domain as time shift, because it takes some time to observe an output. But if we take the Laplace transform, you might want to check out the time shift property of the Laplace transform. You'll see that it becomes an exponential term in the transfer function. Therefore, you can see that there's an exponential term added to the transfer function. So this means that we will have a transfer function with the poles and zeros as usual. And then we will also have an exponential term. And this exponential term will model the delay or dead time portion of the system. And we will try to look at such systems and try to design also controllers. So there are two steps to this. One of them is to analyze such a system. And of course, the second would be then a controller design or synthesis. So let's begin with the analyze step here. So if we have such a transfer function, if we open up Simulink, it is very easy to just drop a transfer function, connect a exponential term or delay to it, and we're good to go. But if we have such a transfer function that has delay in it, how can we use our control system toolbox as usual? Because I want to apply step to this transfer function, and I want to see what is really going on. So, and keep also in mind that this is a transfer function, therefore this is a relation between the input and output. If we are using MATLAB and the control system toolbox, what we can do is we can just use a property here that's called IO delay. So this is a delay between the input I and the output O, so IO delay. And then we'll give the amount of delay that the system has. For example, we have 2 seconds of delay because this term here, this is the time delay constant. So TD maybe, or tau D. So therefore, we have 2 seconds of delay for this system. Now, what would I expect if I apply step to such a system? And I also want to take this apart. So let's have GS on its own without the delay part. And let's say G delay, the delay transfer function here. And let's define this transfer function as this. So I've basically defined a transfer function that has no zeros, no poles. It's just a static gain 1, but it has the IO delay property equal to 2, which means that this is pure delay in this case. So what I really want to do is I want to get the step response of such a system, but I also want to look at the delayed version. So let's say G delay. So GS times G delay should have delay in it, and this is just the pure transfer function. So let's plot them. So plot TY, maybe black, and there we go. So let's look at this. So what do you expect? What should we see? We have a transfer function. We take the step response. We have the transfer function times the pure delay, 2 seconds of delay, and we again apply step response, the step input to it. And we want to compare the outputs. So what do you expect here? What should we see? Basically, we should see a time shift, and this time shift should look like this. But let's see. Okay, let's increase the amount of time. There we go. Now, since the system has, let me find it back here, has two real poles, this is basically an overdamped transfer function. Therefore, we have no overshoot. We may not be able to tell what the settling time is, but we have a system. And we can also see that the DC gain is basically 12 divided by 24, according to the final value theorem. We can see that it is 1 divided by 2, or half. So therefore, we have 0.5 steady-state gain. We kind of can plot this step response on our own, and adding 2 seconds of delay does indeed shift the response. It's just shifted. So it does not rise from 0, it rises from 2 here. So we will be interested in such systems. And you can see here that using the IO delay property, we're able to define such systems. So now, what if we, since we have the transfer function here, what if I want to, let's say, plot the root locus? Because I have a system, I know the poles and zeros, I can plot the root locus in order to, for example, design a p-type controller. So what about that? So let's open up another figure, and let's call the root locus command. But we should take this gs times g delay, because I'm interested in the delayed version here. Now, you can see that the root locus command cannot be used for such systems. And the error message here tells us also to use a command called Putty. So why am I not able to plot the root locus of gs times g delay? So what is the problem with that? So any ideas? We are not able to plot the root locus here. Why? What did really change? Don't we have any poles and zeros? This looks like GSG delay. We have this, and we're not able to plot a root locus. And there might be a more interesting thing if we try to come up with a p-type controller. So let me take this here, and let's define, as usual, a closed loop using that. GS times G delay. So I've randomly picked a p-type controller, a gain here, and I'm trying to calculate the closed loop here. So let's run it again. We have K. Oh, I did forget to write comma 1. Okay, TS, there we go. Now, for some reason, MATLAB did change the transfer function into another model called state space. Maybe it's possible to convert it into a transfer function, but it seems like that also doesn't work. So if I have a delayed system, I'm pretty much in trouble. I can only apply step. I can, of course, also apply body. So GS times G delay would work, because body does not take into account if it has a transfer function. If it is a delayed model, it doesn't really look for that. If you remember, we've talked about the body plot. You're just applying a sinusoidal input, changing the frequency, and look for the output, and you will look for the gain change and the phase change, and you will plot it versus omega, the frequency. So it's possible to do that with this. But We cannot look for the closed loop transfer function. We are not seeing it in the transfer function version. We can just see a state space model here. Yeah, we're pretty much in trouble. So let us look at this closed loop here, but let's use the symbolic toolbox because I can get an expression for that. So let me just take this. We should define it here, GSS. This is 12 divided by s plus 4 times s plus 6. Of course, we have also the delay part. Maybe we should include that. So let's say times exponential minus 2s. That's it, maybe 2 times s here. So we've basically defined the transfer function using the symbolic toolbox. Let me just rearrange stuff here. There we go. And instead of using this command, what we can do, we can just go ahead and use k times GSS and then divide by 1 plus k times GSS. So maybe we should also simplify stuff, or maybe we should use GSS and maybe also pretty in order to see a prettified output. So there we go. Now, even though I've called the simplify function, maybe we should try simplify fraction. Maybe that will work. Yeah, that kind of work. So there we go. If we have a system with delay, we get this output here. And it is interesting because we have this exponential term here, and you might want to rearrange this and take this here. So it will be 12 times e to the power of minus 2s divided by 24 plus 10s plus s squared, and 10 plus 12 times e to the power of minus 2s. So if we divide by this term, we'll get a term here. If we don't divide by that, we still have an exponential term here. So at this point, we have a problem. The reason for that is the following. In order to calculate the poles of such a transfer function, we take the characteristic polynomial. And the characteristic polynomial is by definition the polynomial that appears in the denominator. But here the denominator is not a polynomial because by definition a polynomial uses just the s powers and their linear combination. But we have a nonlinear term here, the e term. So therefore, this is not a valid transfer function, or we cannot acquire a valid characteristic polynomial. So all that stuff that we've talked about the characteristic polynomial, about the stability properties, about the fact that we will choose zeta and omega and will assign them to certain values and try to increase the dominance factor, all that stuff is not applicable to this system because we don't have any polynomial here. We have a nonlinear term, and that's it. It's depending on a frequency variable s, but that's the only thing that we have. So what now? Well, as any engineer would come up, I'd say we might use a Taylor expansion, because using maybe the second order or third order Taylor expansion, we would get the s powers here. That would be one choice. We could go that route. And as far as I remember, there was such a thing in your midterm exam. But there's another and even better method to overcome this, or to try to overcome this problem. That's called Putty, and we will talk about that in a moment. But there's also another possibility that will come up in the upcoming week or upcoming lesson in the laboratory session. And that would be to use frequency domain methods, because I can plot the body plot of this. So if there are controller design methods using body plot, then I might use this transfer function, its body, to design a controller. So that might be one route. Or you should approximate e to the power of minus 2s in this case. So next lesson, we will see how to maybe do that or talk about the frequency domain methods. You can then apply all of those things that we will talk about to this transfer function. Or in this lesson, we will see to use the Putty approximation to overcome the problem. And let's do the Putty approximation. The Putty approximation tries to come up with a valid transfer function that we can use, that we've learned to use up to this point. We were using the characteristic polynomial and all sort of stuff to design controllers. What if we can somehow approximate the e to the power of minus 2s term and then get a valid characteristic polynomial, and then just design our controller as usual and go ahead and apply that controller to this system. So the Putty approximation is therefore very useful in this case, and it is defined as follows. Since this is an approximation, it has a degree of accuracy here, and as you might already expect, increasing the order of approximation will give you better accuracy or result. So the first order Putty approximation is an approximation that uses poles and zeros to model the e to the power of minus tau s part, which is nonlinear. So what it does is it takes the time delay constant, takes half of it, and places a zero in the right half plane. And then we will also have a symmetric pole to it. So one pole and one zero should somehow model e to the power of minus tau s. Of course, we have the symbolic toolbox, or we can also use the control system toolbox. Let's see, what if I take e to the power of minus tau s and substitute into this the first order Putty approximation. And let's see how maybe the step responses will relate, because we come up with a transfer function that has no delay in it, but it should look like a delayed system, or it should behave like it. So let's see. Now, it is actually pretty straightforward. Let me comment this out and let me get rid of this first stuff here. So, let's say Putty, and since I'm using the first order, it is quite easy. What you can do is you can just take GS times, and this is the pure transfer function part. All the poles and zeros will be there. They will be preserved. But the only thing that I'll do is I'm just going to add minus 0.5 times, let's say tau, and since it's symmetric, I'm just going to get rid of the negative sign here. So you can see minus 0.5 tau s, this is the s term, and the symmetric, and the constant term is 1. So therefore, this is basically the Putty approximation. Instead of having g delay times gs, we have gs times this approximation. And let me just quickly copy this and take everything back. So now let's look at the delayed output, and let's say first order Putty approximation, just use GS or GPutty1. And that's basically it. Maybe we should also assign some string to it, display name. This is basically t, y, so this is the system. This would be then the first order Putty approximation. But of course, we have to change this into t1 and y1. So there we go. Now, of course, we didn't define tau. Now let's get rid of that problem. tau equals 2. That's it basically. So let's use tau instead of this, and I guess we should be good to go. There we go. Now, if looking at this comparison, one might argue that this is a good approximation, and I would agree. The first order Putty approximation for the step response does not really look alike. But looking at this approximation, we can see that there's a certain property that we're using here. If we apply a input to a transfer function, it will respond at 0 because it has no delay. But if we have this inverse or this undershoot here, then we will cross back here 0, and then we will rise to the response or to the DC gain here. So we're kind of using this 0 that we've placed on the right half plane because it will result in undershoot, and the time that is wasted here should somehow model the delay here. So that's kind of the strategy. But you can see that for the first order approximation and for this system, this doesn't work that much because, well, the behavior is not as we want it to be. So, of course, the first thing would be to increase the order here, and let's do that. Let's increase the order, and there's also the second order part. It shares the first two terms, but we will add t squared divided by 12 s squared to that. So let's do that. Let's have gs Putty 2 tau squared divided by 12, and we're again good to go. Now, can you see where the poles and zeros are? Because it's kind of important. Now, let me maybe show you this part here. So where will be the zeros and poles placed? You can see that this, for example, has positive coefficients, and for a second order polynomial, if we have positive coefficients, we can safely assume that the poles are on the left half plane. So we will have two poles and they will be on the left half plane. And this minus sign here will help us in order to determine how many sign changes here are. So positive, negative, and then again positive. So you can maybe use the root tabulation here, or you can also see that minus here gives us a sum, and we can see that they have basically the same sign here. And the multiplication has also the same sign, so they should be on the right half plane. So these are on the left because their sum is negative, but here we have a positive sum, so therefore 2 on the right half plane, 2 zeros on the right half plane, 2 poles on the left half plane. So we're basically adding zeros on the right half plane and poles on the left half plane, and they are symmetric. So that's what we have up to this point. So let's assign another color. Putty 2 and Putty 2. So there we go. Now let's see how well this performs here. Now you can see that the red line here shows us the second order Putty approximation. And again, it is not really a good one. Again, we have some issues. One of them is that the blue one here somehow modeled the delay as, let's see, approximately 1.12. So 1.12 seconds of delay was modeled using the first order Putty approximation. Now, if we use the second order, we can see that it is 1.56, which is not exactly the value 2 that we were looking for. And again, also from the delay time here, we can see that the behavior is again not the same. But you can also see and maybe assume that if we increase the order, the amount of zeros on the right half plane and poles on the left half plane, this should somehow come to this point and meet this point at 2, then it would hopefully behave like it should be. So again, we have to increase the order of approximation. In order to show you, I have used the first and second order approximations, but MATLAB can help you from here. So it will take from here. So instead of using the approximation, you might not remember it, or it will become complicated. You can also take the 10th degree of approximation, then we will work too much for it. There's a command for this. So if we give it the transfer function that has IO delay in it, we have a command called Putty, and you can give the delay part and the order of approximation. So what we can do here is that we can use a higher order here, maybe 10, maybe 12, and see what's really going on. But in order to do that, I'll update my plot and my code here. What I really want to do is I want to compare the poles and zeros. I want to see where the poles and zeros are placed. So therefore, let's have that. We can also, by the way, just directly give it the delay part here, GS times G delay, and take the approximation here. Let's call it that. So I want to look for the approximation. I want to get the step response. So let's have that. GS times G delay. So this is the original system. Then we have the, for example, second order Putty approximation. We get the step response. Instead of having this, let's create a subplot side by side. And this would then be the step response. And also change maybe this. So basically, I want a for loop here. Directly use that. So for I1 up to, let's say, 4. I want to get the Putty approximation. I want to get the step response. Then, well, we should use that here. Maybe this is also a one-time thing here. And x2. And I also want to look for the poles and zeros. So let's use the pole zero map command, pzmap. Give the box here and then plot the real part, x2 of C poles, and then the imaginary part of C poles. X, maybe line width 2, and also the zeros. Of course, this is 2. This is basically not needed. And this will be the zero map. And x2 equals GCA. There we go. So before I run this code, what I also want to do is I want to calculate a certain color for each approximation here. Maybe now this is not really important, but it will become in a moment. So maybe let's first run it and see what's happening. I guess, didn't the thing here. Let me see. Oh, X1. Yeah, we kind of have what we are looking for. 1, 2, 3, 4. That's good. But we're not really able to see what's really going on. Therefore, let me introduce you to the color here. So let's have a bluish tone, and it should be done like this. And we'll use the color for each drawing. Of course, it's not really needed, but I want to show you how this behaves. So therefore, let's see. There we go. Now, we kind of see we have a better view on stuff. Maybe not here on the pole zero map, but yeah, let's see. Now, if I zoom in here, for the fourth order, we have this kind of behavior here, and we can see that they get closer to the original response here. But also, it's not really good to see here, so maybe we should just directly change this into 4. If we do this, then we have the fourth order approximation. Now, this is a good approximation if you don't really care about these little peak points here. But other than that, we have a delay of 1.84 seconds. And from that point, we can see they are getting closer, basically. So I can also increase this here, maybe 40. Yeah, that should also be 40. Oh. Now you can see that we cannot distinguish the original response and the approximation here. But you can see that there are basically still peaks. Let me just zoom in better. You can see that we have lots of peaks. We're basically trying to spend some time before we start. So we have 2 seconds of time to waste, and we use these pole zero pairs in order to accomplish that. Once that's done, we just have the actual response of the poles. And it would be very painful if we try to use this approximation to design a controller, because keep in mind that from this point on, we will use a transfer function. But the approximation itself, what gprox, I guess, has too many poles and zeros. So it's not really possible to display it. So you can see there are too many poles and zeros. So practically, it's not possible to design a controller for such an approximation. This is a 42th order transfer function. So yeah, with 40 zeros, of course. That brings us to the following. If we want to design a controller and if we want to have a good approximation, we should use a higher order. But the limitation here is that too many poles and zeros will also prevent us from designing a controller, because we have a certain thing in our mind. Namely, we want to try to have a certain dominance in order to have good behavior. So therefore, you should pick the least possible, maybe the first order one, try that out, design a controller, apply it to the system and see if it works. If not, you should increase the order, let's say 2, and try it again. And if that's, again, not sufficient, increase 1 order more, 3, 4. So there's kind of this iteration going on. You should start with 1. And at some point, if you're happy with the controller and the behavior of the closed loop, then you're good to go. Now, theoretically, for the delay, we have, and if we use the Putty approximation, infinitely amount of zeros and infinite amount of poles. Therefore, we are not really able to plot the root locus of the delayed transfer function or pole zero map. Therefore, we are just basically using 2 or 3 poles in order to approximate the overall behavior here. So, and the first task of today was to compare all the step responses. We did go up in order up to 40, but it would be, I guess, it would be a good idea to maybe use 4 in this case, because that was a good approximation. So this is maybe a good approximation, but still we have 4 poles and 2 original poles, which brings us to a 6 order system, and we have 4 zeros. So yeah, also not really that good. But we will try to design a controller to this system. So now there's a question where we will look for the stability interval of a p-type controller using the first order, second order Putty approximation. So let's attack that. Let's start with that. Let me just create another script, copy the necessary parts here, maybe this part. Yeah. So what I really want to do is I want to look for the p-type controllers and the stability of p-type controllers. Now, I have the system here, transfer function, but what I should really do maybe, let me see, maybe we should just create a function that will convert TF to sim at this point. And the reason for that is the following. I don't really want to type out the approximation itself. I will just use a function that converts the symbolic or the transfer function here using Putty. So I can use Putty gs times g delay. But I want to use TF to sim in order to just generate the actual plant that I'm going to use instead of that. So this is actually a very simple function, and let's say GSS, let's call this TF to sim. So it takes in a transfer function GS, it will convert it to a symbolic expression, that's it. So let's define sims S. Now using the transfer function, I can use the numerator here like this in order to get num. So basically the numerator coefficients. I can also use then denominator. This is the equivalent of num then in the symbolic toolbox, but we are using basically TF objects. So let me just, did we call it here? Yeah. So if I call this, yeah, we didn't assign something here, so GS equals 1. There we go. Now you can see that this is basically the numerator. We also have the denominator, but you get the idea. Now, 1, 2, 3, 4 items in this vector, which means that we have s to the power of 3, s to the power of 2, s to the power of 1, and s to the power of 0. So there's the constant term. If I look for the length of this vector, subtract 1, I will get the order. So therefore, I can directly determine the order, length of, let's say, then of the denominator, and take 1 out of it. So at this point, what I can do is I can just create something, and s equals 0. And the idea is the following. I can loop through each coefficient, or we can also maybe do something like this, plus 1, depends on you. So I will use then the ith element of then, and we start with the highest order term. So this would be then s to the power of something, and I'm going to well, we will also have the s here. This would be added to the s. So I'm just using each coefficient and its corresponding power and generate the symbolic expression. So yeah, we have the denominator I, which would then mean that we have the ith power, let me see, the nth power minus I plus 1, I guess. Because if we have n plus 1, it would be n plus 1 minus n plus 1. So we would get 0. If we have 1, it will be n. So if we also do this for the numerator, using the numerator, the ns term, and then also num here, and then we're left with ns divided by ds, and that should be it. Let's see if it works. So you can see that pretty GSS, and yeah, we have to compare them like this. Let's have the first order Putty approximation. So let's see. Oh. There we go. Now minus 12s plus 12 minus 12s, basically minus out of the parentheses, but it's the same. S cubed, 11s squared, 34s, and 24. Seems like working. So now this was just to use the Putty approximation. You can just look up the Putty approximation and then use that. It's not really that difficult. We have the expression for 1 and 2. And yeah, now I want to look for p-type controllers and I want to look for stability. So the best way of doing it would be possibly to define sims k. It is a real value, and then GSS divided by +1, and then I don't really need this part, but the characteristic polynomial would then be num then. Now at this point, I'm going to also substitute omega, s equals j omega, and then take the real part, imaginary part, and then solve it basically into PCS instead of s 1i times omega. Now the problem would be to take the real part of p omega, equate it to 0, and then also the imaginary part. And let's solve it. And let's see. So we have 3 solutions. K-val equals double, and then solve out K-val. K. The same goes for omega. Let's have the index. Let's look for omega n, omega val greater than or equal to 0. And then k-val equals k-val index. Same goes for omega n val. Omega val. So omega val, k-val, there we go. Now we can see that there are 2 crossings. One is at omega, the other one is at 2.19 frequency. The gain corresponds to -2 and 2.43. So that's one value, 2.43. Seems like the interval. So let me maybe note it here. Take a note here, 2.4306. And -2. So -2 k this for Putty approximation 1. So is this correct? That's basically the question here, because the problem here is the following. We have a transfer function and we have the delay part here. And in order to calculate the characteristic polynomial, I have to use the Putty approximation. But since this is an approximation, and since we've seen the difference between the step responses of the original response and the approximation, I doubt that this is a good value, or this is a valid value, because this is an approximation. This is not the actual system's representation that I'm using here. So therefore, I'm not really sure if the system is really stable for this p-type controller. But what I can do is I can just look for it. I have the k value here. So what I can do is I can just directly use feedback on gs times g delay. Instead of using the approximation, I'm using the actual delayed system. 1, and then we have, let's say, K1. And the value of K1 is 2.4306. Feedback. So did we use any figure or no? I'm not really going to look for the detail, but that's enough. So I could have used gs_approx here, because that's the approximation that I've used, but it would not make any sense. Because I already know that, because I have used this in order to come up with the controller itself. But I'm not working with the approximation. The actual system is here. So I should apply the p-type controller to the actual system that has delay in it, not to the approximation. That's really important about the Putty approximation. Most of the time, you will forget the fact that you are not using the approximation. So imagine that you're in the laboratory and you have a system that has delay in it, but you're just taking the model on pen and paper. You just use the Putty approximation. You come up with a controller value, let's say 2.43. And you want to test it. You want to verify the fact that this is really the stability margin, the value that gives us the stability margin. You have to use the actual system in the lab, not the model that you've generated. So, therefore, let's see what happens. Now, as I've suspected, the system is not stable. So maybe we should decrease it a little bit, maybe 2.9, just about there. Still not it. Now, it seems like using the Putty approximation and looking for the gain value that gives us stability, the stability margin, does not give us the stability margin. If I use the approximation, it will give me what I expected. So maybe we should just generate that. Instead of using this, I'm just going to use the approximation. So comment this out. Let's try it again. Now you can see that the approximation itself is marginally stable. There's no problem in that. But the actual system is not. So this means that the Putty approximation itself is actually dangerous, because you're in the lab, you've designed a controller, you think that it is stable, but you didn't check, you didn't verify if it's really stable by using the original system that you were interested in. And suddenly, if you apply that, you see that there's instability. So you should be careful. So what can we improve? What can we do so that we get maybe a better result? Maybe a result that works. So, well, the first thing that comes to mind maybe would be to increase the approximation. And this was basically expected because we have used the approximation and we've looked for the first and second orders, and we've seen that it's not really a good approximation. Therefore, I don't blame the Putty approximation because it didn't really promise us that much. So therefore, we see that, yeah, it's not a good approximation. Therefore, it doesn't work. maybe increasing the order should help us. So let's see. And just to be sure, GS approx, I guess. Yep. You can see that I have used the second order approximation because there are two zeros. We originally didn't have any zero, and then there are two poles, and then the two original poles. And again, we have to look for k-val and omega val. Now there are two valid points here, two crossings. And -2 is again there, but now we have 2.16. What was the original value? It was 2.43. Now, increasing the approximation here, this was -2, I guess. If we increase the order, we get 2.16 and 59. This is the second order Putty approximation. And yeah, now let's define K1 as 2.1659. And of course, get rid of this. So the actual system with the gain value 2.16. Now it seems like it's still not stable, but this might also be because of the fact that we have used 2.1659, maybe just about that gain, which we kind of get close to the actual result, it seems like. But again, the second order approximation didn't give us the exact value. We're just maybe approaching it, but we didn't get the exact value. Now let's increase that one more time. Third order Putty approximation. Let's see what's really going on here. Yeah. K-val, omega val, and 2.1538. 1538. So maybe we should just use 2.15. I guess this is the point where we can stop. We can see that it kind of gives us the stability margin here. For 2.15, the system becomes almost marginally stable. We can just basically also assume that this is the marginal stability point because, yeah, it's close enough. What have we seen from here? Using the Putty approximation, and you can also see that it was not 2.15 exactly, but we've just rounded it. What we've seen is the following. By the way, did you notice that the amount of frequencies here and the amount of results here did increase in by the way? So we had just 2 values for the first order, 3 values for the second order, and then 4 values for the third order. So it keeps on increasing. It gives me more and more results, more and more crossings. And the reason for that is basically we have 1 0 on the right half plane, 1 pole on the left half plane. And as you already know from the root locus plotting method, that all poles try to go to zeros. So if you have 2 or more, if you have 3 zeros on the right half plane, 3 poles will eventually go to those zeros. So therefore you will have j omega crossings because you start on the left half plane and you end up in the right half plane. What do you expect? Well, basically a j omega crossing. So it makes sense that if we increase the Putty approximation order, that we get more and more omega values. So that's important. And yeah, what can we say about a system that has delay in it, and if we're using the Putty approximation? Well, we cannot say much, but we can say the following. Instead of giving you the stability interval, because it's not guaranteed, the approximation might be marginally stable, but the system might not be marginally stable. Therefore, if you use the Putty approximation, you get kind of the unstable region. You know that for greater than, let me show you the values, greater than 2.42, the system is definitely unstable. But you don't really know if it's between -2 and 2.42, if it's stable or not. You're not really sure about that, but you are sure that using 2.43 and higher values, the system is not stable. So keep that in mind. It doesn't give us really the stability interval, but it gives us the instability interval, sort of. Therefore, if you're looking for stability analysis, the Putty approximation kind of helps you, but not really, because these are not really high values, and you can just maybe look for it on your own. Instead of using this much effort, you can just build a for loop, try the values, and look if it's stable or not. Putty didn't really help you out there. So what about designing a PI-type controller? I guess we could transition to this, but maybe we need a little break. Should we give a little break? Ufak bir ara verelim mi? Tasarıma geçeceğiz çünkü. Okay, let's continue. Now we've looked at the Putty approximation, some orders, and we've looked at the stability interval. And let me again remind you the fact that if you're using the Putty approximation instead of getting the stability interval, you kind of get the instability interval because it doesn't guarantee you that if the approximation is stable, then your system will be stable. There's no guarantee. But if your approximation is unstable, then your system is unstable. So that's for sure. Now, we were left at the point where we were looking for a PI controller design. So let's try to design a PI controller. So 10% overshoot and nothing else. So yeah, overshoot is 10%. Let me just copy this, maybe this, and this should be enough. So now we have the system, we have the similar expression, and then we will have, of course, zeta, which is minus log overshoot divided by the square root of pi squared plus log overshoot squared. Zeta value. Now, before I go on, since we are looking for a PI controller, let's define Kp and Ki. They are real values. Let's have the controller itself, Kp plus Ki divided by S, and then also the closed loop, FSS times GSS, and 1 plus that. Also maybe PZS and PCS, num then PSS. So let's run this. Zeta is this, we have PCS. So maybe we should look for the coefficients here. Now, yeah, let's see, S to the power of 6. Of course, we did use, I guess, a further approximation. And as I've told you before, we will use the first order one. We will start with 1. So in order to solve it easily. So PCS looks like this, and we have a fourth order characteristic polynomial, I guess. The system had 2, and the system had 2. The first order approximation adds 1. So let me just quickly check. Yeah. Since we have also the controller itself, you can see that the approximation did add 1, the controller add another 1. So therefore we have a fourth order closed loop. So you can see that even using a first order approximation gives us much trouble because we have a fourth order 1. If we increase the order, it will get worse. So now, yeah, we have to define omega n because we don't know what that is. And then we will have a and b. Those are also real values. The residual polynomial, as usual, the desired polynomial, 2 times theta times omega n times s plus omega n squared. And then s squared plus a times s plus b. So the problem then would be so do we have higher order term? Nope, so we don't really need to normalize now. So the coefficients of PDS times PES, all the S coefficients equal to coefs of PCS. Let me quickly print the equations here. Go. Now, we have A, we have B, we have omega n, we have Ki, and we have Kp. So we have 5 unknowns, and we have a -1 here, so we should normalize, by the way. 1, 2, 3, 4 equations. So let me just get rid of that, by the way. So all equals coefs of PCS, all the S coefficients, and pole should be equal to pole divided by the first element here. And instead of using this, we should equate it to pole. There we go. Now you can see we have 1 equals 1. And what we've basically done is we've multiplied -1, all these terms with -1. So that's basically it. Now, we have A, B, omega n, and Kp and Ki. Now we have 5 unknowns. What we can do is we can just go ahead and use omega n maybe as the free variable, and then try to design a controller. But for the sake of simplicity, just for this example, I'm going to pick omega n so that it works, because that's not really the point of our discussion here, just to cut it short. But usually what we have to do is we have to choose one parameter and look for maybe a tabulation or maybe a root locus method here. But I'm going to skip that part. So let's maybe, for example, assign omega n equals 1 and try to look at the problem. Now, I can see that A would be a positive value. So that's a good thing, I guess. And other than that, since A is a positive value, that's roughly 10. So 11, it seems like we could come up with a stable solution. So we have A, B, Ki, and Kp. No omega and no zeta, so we can just directly solve this problem. So let's have Kp val sol.kp, but we should convert it into double. And then Ki. So maybe we should also check out what B is. And A is, of course. There we go. Now, at this point, I'm basically ready to check if the controller works. So let's define a controller. And Kp val, Ki val, that would be the PI controller. And then we will look for feedback, Fs times Gs, 1. Now Gs, props, I guess, yep. So let's look for the response. Yeah, we can also check step info and TS. There we go. We have 15% overshoot and we have 6.49 as a settling time. Seems like we can improve that, but yeah, maybe a faster system. Let's try a faster one. Maybe omega n should be 0.5. Not sure. Again, I'm just trying to come up with a fast and nice solution. Seems like overshoot is 10, settling time is a little bit slower, but yeah, not really that big of a deal. Let's look at PZ map. Yeah. Let's look at the pole zero map. We have a 0 on the right half plane. That's already because of the approximation. We have 2 poles here, and one of the poles is at -4, at -5, and then we have a 0 here. Of course, we should use tabulation or, as again mentioned, the root locus method in order to optimize the dominance factor. But yeah, I've skipped that part for now. We can see that this is technically something that we can use because it has the overshoot value that we are interested in, and it has a certain settling time value. We didn't really limit that. But let's close everything. Run 3. Now, this step response is not the actual step response that I'm interested in. Again, this is the approximation. I have no guarantee that the actual system with delay will behave like this. So again, you have to be very careful about this. You're just using an approximation, and of course this approximation should work. This is already expected. We should check out what happens if we use the actual delayed system. So instead of using this, what I'm going to do is I'm just going to use GS times G delay. GS times G delay, yeah. If this works, then I'm good to go. So let's call this TS sys, maybe, the system. Let's calculate the system response. And let's plot that too. So maybe like this. So here I can see that the overshoot value is not, again, 10%, but it's 13.9, so roughly 14%. Of course, for now, I'm okay with this, but it might be the case that I'm looking for exactly 10%, then I might maybe improve it a little bit. But, well, basically using this approximation, since I have 10% here, I cannot improve on that. What I have to really do is I have to increase the Putty approximation, the order of that, because a higher order means better approximation. Better approximation means higher accuracy in this case, because there will be a difference, and this difference is inevitable because, yeah, it's just modeling it using the first order one. If you increase the model order, then it would become better, but then you have to be careful because you will have more poles and zeros to take care of. To have a higher precision, you have to work a little bit harder. In this case, I'm going to be happy because I'm trying to make a point here instead of designing a controller and a closed loop. But you can see that the black signal here shows us the approximation. And the blue one is the actual system behavior, and the model seems to be having a higher overshoot value. In this case, it's not really that big of a difference, but it might be the case that this increases because it might be 15 or 20%, and you have to just increase the order of the approximation. There will be some error. In this case, it seems like that using the Putty approximation, we are not really that successful in obtaining the stability interval for p-type controllers, but using the approximation, it seems like it is not really that bad to design controllers. But it's a bit hard because you have to work for it. You have to take care of all the poles and zeros if you're looking for dominant pole placement. But other than that, it seems like this is a good approach here. You can use the Putty approximation. Of course, we can go on and try to increase the Putty order here, but it's not really the main focus of our talk today. So, yeah, we have basically designed a PI controller for the system. But that's not the only thing that we can use here. There's something called the Smith predictor that I want to talk about. Now, we have used the delay. We've seen that using IO delay, we are able to define such systems and examine them. We cannot use the root locus on this or the pole zero map because it has infinite zeros and infinite poles because there's this delay term. Other than that, we've seen that there's an approximation that we can use, which helps us in order to obtain a transfer function that we can work with, but that has some limitations or difficulties to it. Now, there's a special connection and a special structure, basically, and a method that's called Smith predictor that we can use for systems with delays. And instead of now using the VS Code environment, I will just show you from the PDF because it will be more effective. I have to write down stuff, but everyone has to see it. So therefore, we'll see in the PDF. Now, in the PDF, I have all the necessary steps and comparisons that I've talked about today. There are also poles and zeros here. You can just check them out. The code is also available. Using different orders for the stability interval using first order and second order Putty approximation results in different root locuses, as you can see here. Well, I've used the direct substitution method where we just substitute s equals j omega and look for the j omega crossings, but you can also do that manually using root locus plots. And also we've talked about the fact that it doesn't give us the actual stability interval, but we can be sure that if the approximation is not stable, the system will not be stable. Now, other than that, we have also some designs here. But I want to talk about the Smith predictor here. Now, here, using the Smith predictor, I may have to try to show you the following. So since we have a controller and a, let's call it model, that has delay in it, let's also say delay. So I'm separating the parts here. So there's an idea that we can do the following. We can just go ahead and, maybe not from here, of course. So instead of using the controller and this forward path here, what we can do is we can do the following. This might look a little bit silly at first glance, but you'll see why it's working. So what we're doing is, let me just connect this here. So there's the summation point here. First of all, this is a negative. So we subtract basically the same branch here. So we have this model times delay, or let's call it directly the model. Let's say GS times delay, so that it is a bit different. Theoretically, GS times G delay is equal to G model. And we are subtracting these two signals here at this point. And not only that, what we also do is we do the following. We have another branch that comes from here that looks like this. So again, this might look a little bit silly. So let me just put in some signs here in order to remind you of the signs here. So this branch here is added, and then this branch here is subtracted. There's also another summation point here. And we're adding basically this branch here. And all are connected to this point here. Basically the control signal at this point. And then we have the usual structure. So basically there's also another feedback path that looks like this. So that looks like this. So this means that we have another summation point here. I'm out of space, I guess. So this is the connection. Here's the reference, and then we have the output. We are just measuring this. We are feeding it back. Here's the negative side, as usual. But here we have an interesting structure. We have the model itself, which means that if it's, for example, an induction motor, we have that motor in our laboratory. But then we are connecting a model that we assume that is equal to. So this is basically the mathematical model, and that's the actual system. So maybe we should call it the system in order to be more correct. So this is the system itself. This is the mathematical model. And we also use the same part, GS here, which has no delay in it as another branch. And we're adding this up. This is actually a special type of control. This is called internal model control, but this is just for delay systems, so systems with delays. And here what we do is we are basically using a model matching controller strategy here. Remember that we were using the model matching controller where we define a closed loop and then we acquire the controller that does the job. Well, basically there we were multiplicative with it. So what I mean by that is we were multiplying with the inverse of the system. So kind of this times GS. So all the poles and zeros were matching each other and getting rid of the effects. And then we were just trying to add the part that is necessary in order to obtain the TDS here. So the loop transfer function LDS. So we were getting rid of all the system zeros and poles, and we were adding the poles that were necessary. Now, this branch is the system. We are getting rid of all the effects of the system, but we are adding the part that is needed here. You can kind of look at this that way. So this has no advantage if you just look at it, but if you try to come up with a closed loop transfer function, then you'll see why this has an effect. And I've already worked it out here. Now, this closed loop transfer function is basically this structure here, but I guess I've called it G0 and then the E term. So let's call it G0. And this is the E term. So something like this. Now we have the closed loop here. You can just check the PDF out or try to obtain it yourself because it's a challenge and it's really nice to do that. But at the end, what you will see as a transfer function in the closed loop is this. And by the way, this is GM, the model, the system, whatever. So we have basically Fs times G0s times e to the power of minus tau s. So basically this here is this here, but also Gm, because we are trying to match this. So this should be the same, ideally. If that's the case, then the numerator looks like this. And then we have 1 plus f times g0 plus f times g0 to the power of e to the power of minus tau s, and then fs gms. So again, the closed loop transfer function does also look complicated, but there's an assumption that will help us here. If the model GM here is equal to G0 e to the power of minus tau s, if these two are equal to each other, then this term will vanish. In order to be able to use this should happen. So the model GM should be exactly equal to G0 e to the power of minus tau s. As it was the case for the model matching controller, where all the zeros and all the poles should be on top of each other. This is the same kind of limitation of this structure. If this happens, you're left with fg0 divided by 1 plus fg0 times e to the power of minus tau s. And the interesting fact about this is the following. We have a characteristic polynomial. If we use GM or G0 e to the power of tau s and use a controller and obtain the closed loop transfer function, you will see that in the denominator somewhere you will have an e term, an exponential term. Therefore, it will be a quasi-polynomial, not a polynomial. Then you might use Putty approximation, etc. But using this special structure and meeting this requirement here, you can just use the non-delay part and design a controller for that and obtain the closed loop. And the only difference will be that your closed loop will be shifted by tau. So we have looked at GS with delay and without delay in run 1 here. If you remember, somewhere here we did that. We have compared the step responses. Basically, in closed loop, we're trying to achieve that effect. We are trying to get rid of all the delay parts in the denominator. We are just going to design a controller for G0, the non-delay part of the transfer function. And then we will use the structure and we're hopefully going to be happy. So you need this structure and a controller for G0 and nothing else. So if that happens, you can see that if GM is equal to G0 e to the power of minus tau s, then these terms will cancel each other out. You'll be left with this, where this is basically the non-delay part. G0 here is 12 divided by s plus 4 and s plus 6. So it's a second order transfer function, and if you're designing a PI controller, you will have just a third order closed loop, and it will be very easy to design a controller for that. Where if we would use the Putty approximation and a higher order one, then we would basically have to deal with 6th order or 7th order polynomials. In this case, it's not really necessary. Here we can see that we're just basically designing a controller for non-delay part, and in the end result, if we don't have the structure here, if we don't use the Smith predictor, and we're designing a controller for a second order transfer function, this would be the step response, but it would start at 0. But using this, we get a shift here. Now, what will be the effect if we have here G0 times e to the power of minus tau s, and the system is not exactly the same? So there might be some modeling errors. Now, this means that we're modeling our system very well. If we do that, then this connection will work. But if there are problems in the model, if it's not really a good model, then you will see effects like this. You will see that, for example, having a different delay value other than the actual system's delay, then you'll see that it starts good, but then it just is not suitable for control. So this is basically a limitation. If you have a slightly difference in the delay, instead of 2 seconds, having 1.8 seconds, then you'll end up in this result here. Now, I highly recommend you to try out this whole structure here. Even if I'm going to do it here on my own, it will not be very helpful, because everyone should really take a pen and paper and try to come up with the closed loop transfer function of the structure that I tried to show you, and then see on your own what the effects are. And also, it's important to use maybe Simulink and then plug everything in and try to see what the result is going to be. Yeah. You can use a Smith predictor if you have a good model, a model that represents the system very well in terms of delay. You can just use the Smith predictor. Don't use anything else. Just go ahead and design a controller for the non-delay part and you're good to go. Build the structure and that's it. It's basically the model matching controller of delay. That's basically it. Now, yeah, there's one more part about delay that I will talk about, but it's not going to be in this lesson. That will be up to the next lesson, and that's basically the frequency domain approach. We can also use systems with delay and the frequency domain in order to synthesize or analyze the system. But therefore, we need some frequency domain aspects. We have to learn about that. So that will be the next lesson. Now,